This is the Algebra 2 lesson for section 3.1 day 2. If you didn't remember, I had said make sure that you have your graphing calculator handy and or the app that we have on the Chromebook for this, because this is definitely one where we get some not so nice numbers and we definitely want to use a graphing calculator to do what we need to do. So for 3.1 day 2, we started in the day 1 talking about finding where the lines intersect and using whether or not it was tables or graphs to figure that out. So our objective here is still to solve a linear system using a graph or table. And the smart bird says I don't want to wake up. There we go. So we finished that up with this assignment. And we get to problem 3. And this one says, oh, you know that stuff that we did with the calculator on the test of 2.1 to 2.5? You have to do it again. So those of you that said, no, I don't want to learn how to do that, well, by golly, you're going to learn how to do that, because we have to know how to do it for this. We have real life data here. And like it says, this is directly from the Census Bureau, and we are going to use that information to figure out an answer to a question, whatever it is that they have. So it says for population, the table shows the populations of New York City and Los Angeles metropolitan regions from the census reports for 1950 through 2000. Now, if you've ever wondered why they do the census is done for a lot of reasons. It has to do with societal programs, like making sure that everybody has, food to eat and all that good stuff. But we also compare ourselves to other countries, and that typically comes from the GDP. And the GDP tries to figure out per person in the United States, how much product are we putting out there, the gross domestic product that we could sell within our most of the time we want to sell it outside of the United States. So this data is really, really important. Now it says, assuming these linear trends continue, when will the populations of these regions be equal? And what will that population be? Now, it is highly unlikely that these two are perfect straight lines. So we've got New York City and we have Los Angeles, and those are both there. And we see these little boxes, and it says we know we have population data for two regions. What we need is the point in time when their populations will be the same. So what we're going to do is we're going to use the calculator to find linear regression models, and those are equations for lines. We're going to plot those lines, and then we're going to find the point of intersection. And like it says, what will X represent? Well, we have to figure that out. And when you see data like this, you try to figure out what are we going to have our 0 year as. So we're going to use 1950 as our 0 year. So X equals 0 is 1950. Like I said, that's usually time, and time usually is the stuff that goes along the horizontal axis or the x-axis. So that means this is 0, and 1960 is how many years after 1950? 10. And then I look to see that that pattern holds. 50, 60, 70, 80, 90, 20, or 20, 2000 there. So they're going up by 10s each time. So those would be my X values. I'll use those instead of typing in 1950, 1960, 1970. And you might say, well, that's not a huge, change, but it makes a difference. We've got some pretty big numbers here. So the next thing we have to do is we have to get this data into the graphing calculator. And this time we actually have 3 different sets of data. So we're going to put these 0, 10, 20, 30, 40, 50s in there as lists of 1. And then we can put the New York numbers in as lists of 2. And the Los Angeles numbers in as lists sub 3. But like it says below there, we're going to do pretty much what the book did, and it said enter all the numbers as millions, so rounded to the nearest 100,000. So the one up there for New York City that says 12,911,994, that we're going to put in as 12.9. And yes, that's going to lose a little accuracy, but we're going to gain a whole lot of time in punching things in. I don't know that that can even be read. So we're going to put that in as 12.9. And then I look at the next one and I think, okay, so this is a 7, but this is a 5, which is 5 or bigger means we round up. So we'll put this in as 14.8. So why don't you go ahead and do your rounding on all of these while I write down mine. So take a peek up there, check those, and make sure that everything's looking good. Because the next thing we have to do is we have to enter this data into the graphing calculator. So, oh, come on, help me out here. There we go. We have to remember that all of this goes into stats, and that's just to the left of the left arrow key. And number 1 is edit. Now, I've got a ton of stuff in here, so the best thing, easiest thing for me to do since I have a ton is just to clear all the lists. And to do that, I can hit second plus, that gets me into memory, and look at number 4, clear all lists. So I'm going to clear that. Now when I go back into stats and edit, see how they're all clear? And I'm going to make sure I go all the way back to list sub 1. Now, I'm going to pause this because I don't think you need to see me typing all those numbers in, but you go ahead and type the numbers in for yours, and I'll type mine in, and then we'll come back together. Alrighty, they are all in there. And now what we have to do is linear regression for both of these, but we definitely want to store it so that later we can just pull it up and graph it and see where they hit each other. So that means that I have to go into stats, calculate number 4, and I want to use list 1 and list 2 for my New York data. So notice it says that I'm using list 1 and list 4. I don't want list 4, so I hit second, number 2, and that makes it list sub 2. And I do want to store this because remember we want to see where they hit each other. So that's going to be variables, V-A-R-S, arrow to the right once for y variables, number 1, and calculate. But the great news about this is if we go to y equals, it stored all of it, absolutely all of it. So now I have to do that again because I want the other line. So that's stats, calculate, number 4. And now this time I want it to use the Los Angeles list. So I want the times, which is list 1, but then I also want list 3. So second 3 gets list 3 up there. And I want this stored in y sub 2. So variables just to the left of the clear key, y variables by an arrow to the right, number 1 and number 2. So now, if we look in y equals, both of them are stored in there. So what I wanted to know was, when are these going to hit each other? And to see that, I'm going to have to graph it. But this is definitely not a negative 10 to 10 thing. So I'm going to go into my window, and I'm going to think about what I had for my x's. And those were years since 1950. So I will try 100 years, 0 to 100. And then my minimum y, yeah, I can start with 0 because that was the population that we had in millions here. So let's see, our biggest one there is 21.2. So I'll try 30 million. And now when I hit graph, my hope is that I can see where they hit each other. Ooh, there it is. I got lucky on the first time. Because if you can't see the intersection, Blinky can't find it for you. So then we go ahead and tell Blinky, you know, we want you to find the intersection. And Blinky is under second trace, number 5. You can either just hit 5 or you can arrow down and then enter 5. Blinky asks us, is this the first curve? Yeah, it's not a curve though, Blinkster, it's a line. So we'll just hit enter. And then, is this the second curve? Yep, it is. Enter. Again, we know they're lines. And do we want to take a guess? No, that's why we're using a calculator. So hit enter again. And Blinky says it will be about 86.8 years later, and it will be 25.6. That will be the y value. So what we have to do is take note of this and write down where that intersection was. because that's what we were supposed to find. So the question was, when will the populations of these regions be equal? Well, that will be 86.8 years later. Now we're not done with that, and that's because it was 86.8 years after 1950. So we would add 1950. So sometime late in the year 2036, and then we'd want to tell them what that population would be. That was our y value. So our y value for this was 25.6. But I want to change this back. Remember, I had to round that to hundred thousands. So I'm going to make this a comma and put my zeros back in for the population so that we could just show somebody immediately what that would be. So the populations will be the same sometime late in 2036, 2037, because remember, this is just a prediction. And it will be at approximately 25,600,000 people. So that's why we're using the graphing calculator for these. And again, we don't know that this is the case, that this is actually happening, that the populations have gone the way that they thought they would go. But we can make predictions then. And that's what big cities need to do, because they need to know, are we going to have enough housing? Now, we'll go to the got it 3. And again, you can try this one kind of on your own and see if you can get it. All right, so I hope you've gone ahead and gotten your 0, 10, 20, 30, 40, 50 on there. Then, when we think about rounding into the millions place again, like the book did, we have to think of this as 0.334387 for San Diego. So that would be 0.3, because remember, we're doing this in millions. So it's like this says 0, 334, blah, blah, blah. So that'll be 0.3. This would be 0.6. This would be 0.7. This would be 0.9. 1.1, 1.2, 1.8, 1.7, 1.5, 1.2, 1.0, and again, think of it as 0. Blah, blah, blah. So we've got that one rounding up to 1, because a 5 after the 9 says we have to round up, and since that's a 9, we'd have to round it up to 10, which would make that a 1. So you can go ahead and put these in your calculator. I'll do the same thing, but I'll hit pause while I do it. All right, if we're in stats, you can see I've got all those numbers in there, and I did second plus number 4, clear all the lists to get them all out of there. And then I went ahead and put in our time since 1950 in years for list sub 1. List sub 2 is San Diego, and list sub 3 is Detroit. Now, these are definitely not as large of populations as we had for New York and Los Angeles. But we'll give it a try, and we'll see whether or not we can graph it with the window we already had. So stats, calculate, arrow once to the right, number 4, and I want list 1 and list 2. So second, list 2, and I want to store that, variables, y variables, arrow to the right once, number 1, and I'm going to override that other data that we had since we're not using it for this one. So y sub 1, enter. Now all that's stored and waiting for me. Now I have to do it again. So stats, calculate, number 4, and now it has to be list 1 and list 3. So go down to your y list and hit second, number 3, and this time y sub 2. So variables, y variables, arrow to the right once, number 1, and I'm going to put that in number 2. And done. Now we go into y equals, stored all of that fabulous information for us, and I'm going to hit graph. Yeah, those populations definitely not as big as the other two. Too much white space. All of this. Blinky could find us the intersection, but I want to see it. I want to have it really clear. So I had way too many y's and probably way too many x's. So my window, let's try 0 to 60. And then again, these were much smaller, so let's try 0 to 5 million for the y's for the population and hit graph. That's better. Still have some white space, but we can definitely see the intersection a lot clearer. So second trace, call up Blinky, number 5, enter 1, 2, 3 times. And Blinky says 40.7 years later, they will be the same at 1.08 million. So let's go ahead and get that information down. There's our population. When were the populations of the regions equal? 40.7 years later. Again, that's not done because we have to add the 1950 to that. Apparently, I'm writing on the little recorder here. So let me move this up. All right, so 0.709. Probably sometime close to 1991 or so. End of 1990. And the population will be, the Y value from our calculator was about 1.1 million if we round like they had us doing before. And again, we might want to go ahead and put all the zeros back on so that everybody could see what that population would be. So if we put all the zeros back on for rounding to 100,000ths, we can see it would be 1,100,000 people. So in 1990, the population will be about 1,100,000 people. Again, really important information. Now on that last one, in fact on both of them, you saw that one of those populations is going up and the other one is going down. And that happens. So they're trying to see when are these two things going to be equal because of that. One going up and one going down. So with those problems, it's going to be total calculator. You know, I'll need to see that what I really want is for a little sketch of what you saw when you had it in the calculator. But you should write your equations down. You should give me a little sketch of what you saw, and then what was the answer to the problem. So that's a big part of the learning objective for this section that we're trying to figure out. When do these systems meet each other? Because each of these was a line, and when we have two or more lines hitting each other, that's called a system. So this one has all of the buttons that we pushed, this page. So in your packet, it should be right there. If you're thinking, I'm going to totally forget what buttons we used here. Everything's right here. Everything was right here. So use that page. Now we have another topic in this section. And it talks about how sometimes they hit each other. We love that, by the way. In math, we love to be able to say we found a solution. So you can classify a system of two linear equations by the number of solutions. So a consistent solution. Now, consistent means it happens all the time. We would love it if we always got an answer every time. So a consistent system has at least one solution. Consistent systems can be independent, which is perfect because that means you get one answer, or they can be dependent. Now, a dependent system is a system where one line graphs right over the top of itself. You maybe don't notice at first that they're the same line because maybe one of them has been multiplied by 2 or something, so you don't see it. But when we graph it, we see that, oh my gosh, these were both the exact same line when we started. So we start with consistent systems. Consistent systems, you either get one answer, which is independent, or the line is right on top of itself, and that's a dependent system. But it's still consistent because we get to say it has a solution, infinitely many solutions. And here's the one we don't like. The lines are parallel. We have to say there's no solution. That's inconsistent with our mathematical thinking. And that's because, again, we like to get an answer. We don't like it when we have to say there are no solutions to this. So we've got a box with the concept summary, and it says we've got graphical solutions of linear systems. And in the first one, we see a red and a blue line, and they hit each other. Perfect. That is consistent, and it's independent because it's one solution. Love that. And now I look at the second one, and I think, what's up with that? It's purple. Well, that's because red and blue make purple. So this was one line right on top of itself. Now that's consistent because we have an answer, but it's dependent because we have the line right on top of itself. Now, parallel lines, that's the one we don't like. We have to put no solution, and inconsistent because they never will hit one another. So down here, classifying a system without graphing, what they want us to do is take a look at these equations and just figure out from the equation whether or not we should be saying it's independent, dependent, or inconsistent. So to do that, we really need to see them in that y equals mx plus b format, because remember, every line has one unique way to write it when it's in slope-intercept form. So 4y minus 2x equals 6, and I want y equals mx plus b. So I want y by itself. I'm going to add 2x to both sides, and I'm going to divide by 4. All right, so there's the top line, color coding as I'm going through this. And this one is 8y equals 4x minus 12, and I realize all I have to do is divide both sides here by 8. Oh, I'm thinking 4 is going into it. 4 goes into 12 3 times, and into 8 2 times. So now here's what I'm looking for. Are they parallel? Yes. Are they the same line? No. So they are parallel because they both have a slope of 1/2. They are not the same line because this is a positive 3/2 and this is a negative 3/2. Well, if they have the same slope, they're not the same line. They have to be parallel. And if they're parallel, we don't like that. We have to put no solutions. So the name for that is inconsistent. Inconsistent. So it's just a piece of vocabulary that we're learning here. It's not like we're learning new math. We already know, watch for the slopes if they're going to be parallel. So for 4a, I have negative 3x plus y equals 4, and I would just add 3x to both sides. And there it is. Now, the bottom one is x minus 1/3 y equals 1. It's going to take a little bit more work. So I'm going to have to subtract an x from both sides. I'm going to scroll this up because it's not going to like that I'm close to that recorder button. And negative 1/3 y equals negative x plus 1. But now, in order to get rid of that negative 1/3, you'd think, oh, I got to divide by negative 1/3. Oh, wait a second, I can't do that. I have to multiply by the reciprocal. So I'm going to have to multiply every term by negative 3, both sides by negative 3. And y will equal 3x minus 3. So now, I'm back to looking at, hey, do they have the same slope? They do. Are they the exact same line? No, they are not. And that's because their y-intercept is a different number. So they're parallel, which means we don't like that. We have to say no solutions, and that is inconsistent. All right, B. 2x plus 3y equals 1. We would subtract 2x from both sides. Divide both sides by 3. And we have y equals negative 2/3 x plus 1/3. The bottom one, we'll go a little faster. That one was 4x plus y equals negative 3. So we'll subtract 4x from both sides. And my first question to myself is, are they parallel? Do they have the same slope? Oh, no. These two lines are nothing like each other. That's fantastic. That means they're going to hit each other at some point. So this would be consistent, and it would be one answer, so that means it is independent. And they probably didn't ask for both of those, but we'll just cover both of them at once. Yeah, they just wanted to know, is it independent, dependent, or inconsistent? But this is consistent. We would get an answer. Those two lines are totally different from each other. And then the last one. Ooh, look at that. They saved us some time. That top one is already y equals mx plus b. So we just have to do some work on the bottom one. Give this one a try. Hit pause. Put it in slope-intercept form. See if you can figure out independent, dependent, or inconsistent. Then start the video back up again. We would subtract 6x from both sides. And divide everything by -3. And we get y equals 2x minus 3. Wait a second. Deja vu. These are exactly the same. Well, they're definitely going to hit each other. They're going to hit each other all the time. That would be infinitely many solutions, but that's not what they asked us for. What they asked us for was to say, hey, this is consistent, but it's going to be dependent, because it's dependent on the fact that it actually was exactly the same line and it went right over the top of itself. So we have definitely met our objectives. We are solving systems, even systems that we have to find the equations for the lines on the calculator for. And we have also talked about some vocabulary that helps us out with that. That's 3-1 day 2. And there is your assignment.